Alright, this is an introduction to limits. And we'll start with the definition. So the limit as x approaches a of a function f of x is equal to L, and this is written as we write LIM for limit. Underneath it we put the x, a little arrow saying as x approaches a, where a is going to be some real number value. Of f of x, we write f of x right after it, and we say equals L, right? So it's the limit as x approaches a of f of x equals L if all values of f of x are close to L. So when I say values of f of x, I'm talking about the y values. So if all the y values are close to L, for all x sufficiently close to but not equal to a. So what we're basically saying here is that you're going to be looking at the x values as you approach some specific x value, which we're calling a. And you're going to be approaching it from both the left and right sides. And we want to really see, as I get close to that value of a, what happens to the y value. So what y value do we get close to? And that's what the L is talking about, the limit. If I was to draw this graphically to give you an idea, a general sketch of what's going on here. If I had an x and y axis, x and y axis, and I was to write this with, here's our value a, some x value, and I have some sort of function which we'll draw in here, and I'll call this f of x. What we're really saying is as the x value is close to a, following this graph from both sides, right, what y value do I approach? The y value that you approach, in other words the y value where this hole is in this case, is what we're calling L, the limit. So the limit is actually the y value you approach as your x values approach a. Keeping in mind that I have an open circle here, it could be a closed circle. But we don't care what happens exactly at the point. We care about what happens when you get really, really close to it, and that's what this is really showing. So let's look at a few examples. So if I said, for example, given f of x equals 2x minus 1. If we were to draw what this graph looks like, it's the line y equals 2x minus 1, so you've probably seen it before. So we'll do a rough sketch here. So here's x and here's y. And drawing the graph in here. Okay, taking a look at this. The sketch for this, right, the y-intercept is -1, so we'd start there. The slope is 2, so I'd go up 1, 2 units over 1, up 1, 2, over 1. Right, you could really keep going with this if you wanted to. up 1, 2 over 1. So you'd have this graph for f of x. Now it's given to you. I'm drawing it here to make sure you remember how to sketch the graph of a line. But I might ask you to find certain things. If I ask you to find the limit, right? So the question will say, find the limit Alright, so find the limit, and let's say the limit as x approaches 2 of f of x. Now, if I was looking at this from this graph, what I'm really saying is as the x value gets close to 2, right? So if I'm doing this graphically, what happens with these y values? So the x value is getting closer to. I'm following my graph from both sides towards the x value of 2. What's the y value I get close to? Well, the y value I get close to is 3. So the limit as x approaches 2 of f of x would be equal to 3. And that would be the answer. So this is doing it graphically. So they might ask you to find the limit graphically. Sometimes they think about it as, okay, if I'm approaching 2, right, sometimes they build like this wall here, and they're saying, okay, what happens when you get closer and closer to the wall? What happens to the y value? Well, the y value would be 3. So that's finding it graphically. They might ask you to do it numerically. If they ask you to do this numerically, sometimes they really ask you to do it kind of by observation. So if I was looking at this numerically, I think I'll do it on the next page. I have a little space to work with. I would say we're going to find the limit as x approaches 2 of the function, which is really 2x minus 1. I'll write it like that. Right? That's still f of x. Numerically. And we're going to kind of do this just using a chart. So we don't even need to know what the graph looks like when we're talking about this. What I'm really going to say is, let's take a look at x values, and then we're going to take a look at what happens to f of x, which equals 2x minus 1. Now, remember what I'm talking about. I want the x values as we approach 2. And I'm talking about it from the left and right, similar to how I did from the graph. Well, you don't want to use like 0 and 1. You want values that are very close to 2. So suppose, we said x was like 1.9. Because remember, we don't care what happens exactly at x equals 2. We just have to care about what happens as you get close to x equals 2. So let's say it was at 1.9. What you're going to do is take, 2 times 1.9 minus 1. And if you did this on your calculator, 2 times 1.9 and minus 1, you get 2.8. Now 1.9 is an x value close to 2. The y value you get out is 2.8. Let's see what happens if you put in 1.99. Well, then we would have 2 times 1.99 minus 1. So we're getting closer to 2. And the y value becomes 2.98. What if we were to put in 1.999? 2 times 1.999 minus 1 gives us a y value of 2.998. Now remember, we're looking for the limit as you approach 2. So here's 2. Now we don't care about what happens at 2. Right? We care about what happens as you approach it. So the x values are getting closer to 2, not just from the lower side, the left side, but also from the right side, come from this direction. So numbers that are slightly above 2, think of numbers, like 2.1. Well, then I would do 2 times 2.1 minus 1, substituting into the function. You get 3.2. We can get closer, right? You could say 2.01, that's even closer to 2. So 2 times 2.01 when we sub in, minus 1, gives you 3.02. And let's just say 2.001. So 2 times 2.001 minus 1, that gives us 3.002. Again, we don't care what happens right at 2, we care about what happens as you approach from the left and right. Now, if these values are going to the same y value, right, these are the y values here, you can kind of see these y values are going towards, well, what number? Well, these are getting really close, 2.9, right, 2.8, 2.98, 2.998. Here, 3.2, 3.02, 3.002. What number are they getting close to? Well, it appears they're getting closer to a limit of 3. So this is where we're getting the limit numerically, right? The limit as x approaches 2 of f of x equals 3. So we did it numerically here. We did it graphically on this page here. But we did get the same result, right? We got 3 for both of them. Because this is a polynomial, right, f of x equals 2x minus 1, this is a polynomial here, we do have a special case where, you know, the limit at the point will be equal to the function value at the point. This is just a note I'm going to write. We'll talk about it more in another section. But, you know, for a polynomial, the limit as x approaches a of f of x is equal to f of a. In other words, if you sub a into the function, you'll get the same value. So what I'm really saying is, in the notation, the limit as x approaches a of f of x equals f of a. But this is only for a polynomial. This is true. We'll talk about other cases where it's true a little bit later, but for right now, know that for a polynomial, that's true. So in our last example, right, so the last example we had the limit as x approaches 2 of f of x plus 2x minus 1. Well, really what that's telling me I'm allowed to do is just sub 2 in there. So I can do this because this is f of 2, in other words, right? That's what I'm subbing in. It's 2 times 2 minus 1, just 4 minus 1, which equals 3. So we get the limit that way. You can only do this, though, if it's a polynomial. If you don't have a polynomial, you can't just substitute in, right? You might have to look at the domain a little bit. And in some cases you'll be able to substitute in some cases you will not be able to substitute in, depending on what's going on. But for polynomial, you'll always be able to sub in the value you're approaching for a limit, because polynomials are continuous, meaning there are no breaks or jumps or holes in the graph. Let's take a look at another one graphically, and then I'll give you some formal definition. So if I said given I'm just going to give you a graph here. So I'll sketch it out. Here's x, here's y. We'll go 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. And we're going to have, this sketch will have a hole at point 1, 2. So an open circle there. And then, you know, the graph here will just go up 1 over 1, up 1 over 1, down 1 over 1. So there'll be a line. It'll look like this. There's a hole at x equals 1, with the y value of the hole being at 2. And then I'm also going to have this point here on the graph, which I'll put right there. So this is still a function, right? This is f of x. We'll call it f of x in this case. Still a function because it passes the vertical line test, right? Even at where the hole is, it only hits the graph once, right? This is part of the graph. This is not part of the graph. But then I could ask you to find the limits based on this graph, right? So I don't know what the function is. I can't substitute in like I did in the last one. You really can't do it numerically. But if I asked you to find, let's say, the first one, the limit as x approaches 1 of f of x. remember the limit is what value you're getting really close to. What y value you're really close to is x gets really close to 1. So I'm following this graph from the left and right side, and I'm following as I get close to 1. Well, what y value do I get close to? It doesn't matter what happens at the point, so don't tell me it's the y value of 4. It's really saying, what am I getting really close to? I'm getting close to the value of the whole, which is really right from the left and right side. As this x value gets close to 1 right here, right? So I'm getting closer to both sides. The y value here is equal to, looks like y value of 2. So the limit as x approaches 1 of f of x is equal to 2, because it's what you're getting really, really close to, not what you're equal to. I don't care what happens at 1 when I'm taking the limit. I only care what happens as you approach 1. So the y value goes close to 2. Let's take a look at this one here. If I said the limit as x approaches 0 of f of x. Well, the limit as x approaches 0, remember this is where x equals 0 is on the axis. Well, coming from both sides, what y value do I get close to? Well, this y value gets close to, looks like 1. It actually, even at the point becomes 1. That doesn't matter. So what happens is you get really close to it? Well, it's going to 1. It's approaching 1. So the limit as x approaches 0 of f of x equals 1 here. And then sometimes I'll ask you about the function itself. Like if I said, what is f of 1? Right? So finding f of 1, that's different than finding the limit, right? Finding f of 1 means what's the y value associated with 1? Well, here's the x value of 1, the y value, well, it's where the closed part is. You don't go to the whole, you go to the closed part, right? It's actually, this part is the function, so f of 1 is equal to 4 in this case. All right, so the limit as x approached 1 was equal to 2. The function value, though, right, at 1 is equal to 4. So these are not equal. And what that's going to show us later on, we'll come up with some formal definition in another section, is that this is not continuous. In other words, there's a jump here. In order for a limit to exist, and we'll write it out formally in a second, the limit as you approach from each side, right, from the left side and the right side, has to be going to the same value. That's how we determined this when we did this part. Right? I didn't just look from one side or the other. So it's important to know that both sides are taken into account when you're looking at the limit. So the next piece we'll look at is some notation that goes along with that. So for our notation, we have, if I write this, the limit as x approaches a. I put this little minus sign. That means from the negative side, which really means from the left side, right? The negative numbers are to the left. So this is really saying from the left side. So this means, of f of x, means to take the limit as x approaches a from the left side. Think of it meaning coming from the negative side. It doesn't make the number negative, it's just coming from the left side of that value a. So from the left side, or the, if I give it this way, the negative side. And similar but different, the limit as x approaches a, little plus up there means to take the limit as x approaches a from the right side. The right side meaning, from the positive side. That's why there's a little plus there, right? So from the positive side. So basically we have a way of describing checking from the left and checking from the right. So this notation is going to be important because it really tells us how to use our next theorem. So this theorem says, that's something we've already done, as x approaches a, the limit of f of x exists and is equal to L if, now this condition needs to be met, if the limit as x approaches a from the left side, that little negative sign there, of f of x equals L, and the limit as x approaches a from the positive side, or from the right side of f of x, equals L. So, in other words, the limit itself exists if, from coming from the left, you go to that y value of L, and coming from the right, you go to the y value of L. So then, we can say the limit as x approaches a, right? So then the limit as x approaches a of f of x equals L. So basically what this says is that if I approach from the left and I get a value, and I approach from the right and I get the same value, then the limit is equal to that value, L, that same y value. If I was to approach from the left and the right and not get the same value, in other words, if these are not equal to each other, then the limit doesn't exist. And that's the last part of this theorem. So we say otherwise, if the limit as x approaches a from the negative side of f of x does not equal the limit as x approaches a from the positive side of f of x, then the limit as x approaches a, so if they're not the same coming from the left and the right, if they're going to different values, then we say the limit as x approaches a of f of x does not exist. And for short, we'll write DNE. We're making sure you understand that. So when you have a limit from the left and the right side, they have to go to the same y value. If they're not going to the same value, then the limit doesn't exist. So, and it really depends on where the point A is, right? So that's really, going to tell us if it exists or not. In the examples I've shown you so far, the limit did exist because I just wanted to introduce it to you. In the next few examples, we'll talk about places where it may or may not exist. So let's take a look here. So in this example, we'll say given h of x equals, it's going to be a piecewise function. We'll say 2x plus 2 for x less than 1, and 2x minus 4 for x greater than or equal to 1. And, we can sketch this to just have an idea of what it looks like. You should have an understanding of what the graph looks like, but just in case, let's sketch it out. So here's the x-axis, here's the y-axis. I'll say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So when you're graphing the piecewise function, remember the boundary point of 1 is going to be important because it's going to tell you where your graph, breaks into different parts of the domain. So at 1, right, if I was just graphing this quickly, when x equals 1, we're here. We'll have an open circle for the first portion of it, so we'll sub 1 into there. 2 times 1 would be 2 plus 2 would give me 4. So at 1, 4, I'm going to have an open circle. And you're going to, you can use this equation would be a line for the 2x plus 2. The y-intercept would be 2. The slope would be 2. So like this, x is less than 1. We're looking at the left. I'm not going to, review how to graph piecewise functions in this part. I just want you to have an understanding of what it would look like. So, right, so to the left of 1, it's looking like that. To the right of 1, right, when x equals 1, This would be 2 times 1 is 2. 2 minus 4 would be negative 2. So you're looking at the point 1, negative 2. This one's included because there's an equal sign here. So you have a closed circle here. And, you know, we can use the slope of this line to continue on. So it's going to go up 2 over 1. You go up 2 over 1 again. It would look something like this. So this is, you know, our function, what we call h of x. Now, I haven't asked you any question yet, right? This is just us sketching what was given to us. So we'll be asked to find and the first one we'll look at is the limit as x approaches 1 of h of x. Now, when I ask you to find that, the first thing you should recognize is that I have to find the limit from the left and the limit from the right. Now, from the graph, you can kind of see what's happening, but you could also do this algebraically. Sometimes they won't even give you the picture. They'll just ask you to find the limit just with the function. So even if we didn't know the picture, what we really need to know is if I'm looking for the limit as x approaches 1 of h of x, I'm looking for two things, right? I'm looking for the limit as x approaches 1 from the negative side of h of x, and you should be showing this, and I'm looking for the limit as x approaches 1 from the positive side of h of x. So from the left side and from the right side. Now, because we're looking at these from the left and right side, I can write this individually now as this is the same as saying this is equal to the limit as x approaches 1 from the negative side of h of x. Well, where's the negative side of 1? Well, the negative side of 1 would be numbers to the left, and numbers that are less than 1. So I know I'm using 2x plus 2 for h of x in this case, because that's where the left side of 1 would be. So it's really the limit as x approaches 1 from the negative side of 2x plus 2. And as I mentioned earlier, if it's a polynomial that you're taking the limit of, you can substitute the value right in. So this is going to be equal to 2 times 2 plus 2, which ends up equaling, 2 times 1. Right, 2 times 1 plus 2 comes up in the x value of 1. So 2 times 1 plus 2, which ends up being 2 plus 2, which equals 4. So the limit from the left side, we know equals 4. From the right side, we'll do the same thing. So we're taking the limit as x approaches 1 from the positive side. Now from the positive side, right, that's when x is greater than 1, so we're using the 2x minus 4. So we can say the limit as x approaches 1 from the positive side of 2x minus 4, because that's the function to the right of 1. And then again, we're subbing in 1 right into here because it's a polynomial, so I can say I have 2 times 1 minus 4, and this equals 2 minus 4, which equals negative 2. So what's my answer? The limit as x approaches 1 of h of x, well, from the left side it approaches 4, from the right side it approaches negative 2. So this limit here, right, as x approaches 1, since the left side is not equal to the right side, does not exist. Right, it does not exist because they're not going to the same y value, right? So just the explanation, you should say this, right? The limit as x approaches 1 from the negative side of h of x doesn't equal the limit as x approaches 1 from the positive side of h of x. So the answer is does not exist. This is why. Now you could have done it by looking at the graph, right? If I look at the graph as I approach 1 from the left side, you can see it goes up to 4. From the right side, the y value is approaching 2. Remember, it doesn't matter what happens at the point, it matters what happens as you get close to it. So from the left side, I'm approaching 1. From the right side, or from the left side, I'm approaching 4. From the right side, I'm approaching a y value of 2. You can see they're not going to the same place, so you know the limit doesn't exist. If you're just doing this graphically, you could just say that. If I ask you to do it algebraically, you have to show this work down here. And a lot of the times, they won't even give you the picture. They might just give you the function to use. So it's important to know the difference. If I ask you this, I said find the limit as x approaches 3 of h of x. You don't necessarily have to look at the left-hand side and the right-hand side, because we know as x approaches 3, we know our graph is continuous here, right? Because this is for all the x's greater than or equal to 1. So this is going to be, right, this 2x minus 4 is the only function I'm going to use as I approach 3. In other words, right, it's the same part of the graph. So if you're looking at this, you could evaluate it from the graph, or because we know that at 3 we don't have an issue, it's going to be going to the same value because it's a polynomial. This is the limit as x approaches 3 of h of x that we're using, because 3 is greater than or equal to 1. We're using the 2x minus 4. You don't even have to worry about the other part, because x equals 3 is only in this part. So limit as x approaches 3 of 2x minus 4. And then you're going to substitute 3 right in there, because you're allowed to do it since it's a polynomial. So 2 times 3 minus 4 is 6 minus 4, which equals 2. So the limit as x approaches 3 for h of x is going to be 2. It's continuous at that point, so you can substitute it right in. It's a polynomial there. In other words, right, looking at this when x equals 3, right, looking at this from each side, from the left side you're going up to a y value of 2, from the right side you're going up to a value of 2. So that's another way of doing it graphically. What if we were to look at another one here? So if I said, for example, given f of x equals this piecewise function 2x, or negative 2x, we'll say, plus 1 for x not equal to 3, and it'll equal 4 for x equals 3. Now we could sketch this if we wanted to. Don't necessarily need it, but maybe it'll be helpful to see what's happening here. If I was looking at this in terms of a sketch, here's an x-axis, here's a y-axis. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You don't have to sketch this every time. I'm just doing this to have you see both the graphic understanding of the limit and the algebraic understanding of it. But if I was graphing this negative 2x plus 1 for x not equal to 3, so when x equals 3, the y value is 4. So when x equals 3, the y value is 1, 2, 3, 4. I'll just put that there. We know it's a closed circle because it's included. Negative 2x plus 1, that's the equation of a line, right? Y equals negative 2x plus 1. It has a y-intercept of 1. So it would be there. The slope is negative 2, so we'd be going down 2 over 1, down 2 over 1, down 2 over 1. But remember, if I'm going down 2 over 1 here, at 3, it's not included, so I need to have an open circle. All right, so down 1, 2 over 1, open circle. And then we know it's a line. Rough sketch, but just have an idea of what's going on here. So we have an open circle at that point, but it's closed up above it. This is the graph of f of x. We don't even need to use the graph, it's just here just for us to look at. If I asked you to find, alright, so say find, the first thing we'll look at is the limit as x approaches 0 of f of x. So you might want to pause it and try this video out as we do each part individually. If I say the limit as x approaches 0 of f of x, well, when x is approaching 0, the function doesn't have a problem point, right? It's negative 2x plus 1 as long as x doesn't equal 3. So as I get close to 0, it's always going to follow this first part. So I can really write this as the limit as x approaches 0 of negative 2x plus 1. And because we know it's continuous there, right, there's no break, jump, or hole there, we can say, all right, I can sub 0 in right away for x. So again, negative 2 times 0 plus 1. So negative 2 times 0 is just 0 plus 1, so this equals just 1. And you can see that from the graph, right? Approaching from the left side, the y value is going towards 1. Approaching 0 from the right side, the y value is going towards 1. So it equals 1. What if I said, what's the limit as x approaches 3 for f of x? Well, remember, when I say limit as x approaches 3, it doesn't matter what happens at 3, right? I only care about what happens as I approach it. Well, as I approach 3, it actually takes on the same function on both sides, right? Negative 2x plus 1 is the same on the left side of 3 as it is from the right side of 3. So I don't have to do this as individual pieces from the left and right, because from the left and right, it's exactly the same. In the previous example, we had different values from the left and right. But here, it's the same on the left side of 3 as it is on the right side of 3. So I can actually just take that limit right away. I can say the limit as x approaches 3 of negative 2x plus 1. Since it's a polynomial here inside of my function, I'm allowed to substitute right in. So this ends up being negative 2 times 3 plus 1, which equals negative 6 plus 1, which is negative 5. So the answer here, right, the limit as x approaches 3 of f of x is going to equal negative 5. Now you might be able to see that here on this graph, but the point being is, you can look at this algebraically. From the left and right side, it's doing the same thing, so you can just take one limit because that covers both of them. And we found the value here by substituting in is negative 5. And then, lastly, if I just said find f of 3, well, what's f of 3? F of 3 is going to be the function value at 3, right? It's not a limit. Well, f of 3, the x value is 3, the y value is 4, so the answer is just 4. So, a function value at 3 is different than the limit value, right? And that's okay. What it really tells you is that the graph's not continuous, and we'll talk about that more in the next section. Let's do one more example for this part. If I was to say given f of x equals 1 over x minus 2 plus 3, and I'll show you what the graph looks like. Alright, so the graph that we would have here, you might not be familiar with it, or you may have forgotten how to get to this type of graph. But the graph of 1 over x typically has asymptotes going along the y-axis and the x-axis. This is shifted to the right 2 and up 3. So 1, 2, 3, 1, 2, 3, 4. So I'm just giving you a general sketch of this graph. Like I said, there's asymptotes. So in this case, there'll be an asymptote at x equals 2 and a horizontal asymptote at x equals 3. And the actual function, kind of follows along the asymptotes but doesn't ever touch them, like this. So the part in the red is the f of x. The asymptote is just there to guide us to the points that we're not allowed to touch, the x and y values that they approach but don't ever equal. So if I said to find, and the first one we'll look at, if I ask you to find the limit as x approaches 2 of f of x. Well, now we're doing this graphically. We don't have a polynomial here. You can't just substitute right in. If you were to substitute 2 right in, it'd become undefined, right? 2 minus 2 gives you 0. So in the denominator, you have 0, you'd be undefined. So we can't just substitute right in. It's not a polynomial. It's not continuous there. So when I'm looking at this graph, what I'm really going to do is I'm going to follow from the left side and the right side, right? So if I said, what's the limit as x approaches 2 from the left side, from the negative side, so I put that little negative there, of f of x. Well, following my graph, this is x equals 2. What's going on with my y values? Well, that arrow there, right, it's saying it's going downward forever. So this equals negative infinity. The y value it's going towards is negative infinity. And that's okay. Sometimes people get thrown off by that. It doesn't have to be an actual numerical value. It's saying this limit is going towards negative infinity for the y values. Also, I need the limit as x approaches 2 from the positive side of f of x. Well, what's happening as I approach 2 from the right? Well, if I follow this from the right, this arrow here is really, it's going upward forever, right? You never actually can get to the asymptote. You can't touch it. So this is going upward forever, so the y values are going to infinity. And then remember, for the limit to exist, what do we have to have happen? Well, the limit from the left needs to be equal to the limit from the right. Well, are these equal? Well, negative infinity is not the same as infinity. So since the limit as x approaches 2 from the negative side of f of x does not equal the limit as x approaches 2 from the positive side of f of x, then the answer is the limit does not exist. All right, so then we say the limit as x approaches 2 of f of x does not exist, because it has to be the same from the left side and the right side. Now you can do that pretty quickly by looking at it, but I want to know the explanation so I understand that you understand what you did. And then we'll do B and C right down here just to save some space. So if I said the limit towards infinity, so if I said as x approaches infinity, right, so it's the limit as x approaches infinity of f of x, what I'm really saying is as the x values go out forever, what y value does this get close to? Well, you're only looking at this top part because, you know, this part of the graph doesn't go over here. When x's go to infinity, we're going way out. Well, what y values are this getting close to? Well, it's getting close to a y value of 3. It's really approaching the asymptote, right? The y value at that asymptote is 3. And lastly, we'll look at the limit as x approaches negative infinity of f of x. So as my x values go towards negative infinity, right, what's happening is you're going way out here to the y values. Well, the y values are getting closer and closer to this asymptote, which is going to be at 3. You don't combine these together. This does not mean the same thing as coming from the left side or the right side. This is really saying the x values are going forever to infinity. This one's saying the x values are going forever towards negative infinity. We're just asking what happens to the y value as that happens. So that was an introduction to limits. You know, we will be talking about limits a little bit further in the next couple of videos. So hopefully this helps give you a good intro, and then you'll be ready for the next sections.